You know, hunting down performance bugs, it can feel like such a drag, right? But what if I told you it's less of a chore and more like solving a really cool mystery? Well, today, we're going to learn how to use one of the most powerful detective tools out there for developers, the Flamegraph. The question that haunts literally every single one of us. Your app is crawling, users are getting frustrated, and you have, well, no clue where the real bottleneck is. It's a deeply frustrating, universal problem. But what if you could see exactly where your code is spending all its time?
Look, for years, the only way to do this was to just sift through mountains of log files. I mean, talk about tedious and slow. It really is like looking for a needle in a haystack. But the new way, with Flamegraphs, it's a whole different ballgame. It's instant, it's visual, and it cuts right through all the noise.
Okay, so how do we even read this thing? The best way to think about it is like an X-ray for your code, or maybe a heat map of your application's activity. Instead of just guessing where the problem might be, a Flamegraph lets you see with your own eyes exactly which functions are the busiest, the most active, the ones eating up all your time.
All right, let's break it down, starting with the most important part, the x-axis. So, you see those blocks? The width of any given block represents the total time your CPU was busy with that function, and everything that function called. It's super simple. Wider is worse. That's it. If you see a wide bar, that's where your performance is getting torched.
Now, what about the y-axis, the height? That just shows you the call stack. It's the story of how you got there. The function at the very top is what's running right now, and the one right below it is what called it, and so on all the way down. It's like a trail of breadcrumbs leading you to the source.
Okay, this is the most crucial takeaway. Seriously, if you only remember one thing today, let it be this golden rule. You're looking for the widest plateaus, those big flat-topped towers. Those are the functions chewing up the most time. And 9 times out of 10, that's where your bottleneck is hiding.
All right, cool. Now that you know how to read the clues, let's put on our detective hats and meet the usual suspects, the common criminals of performance issues you'll find out there in the wild.
So here they are, our 4 most wanted culprits. First up, you've got the CPU hog. This is just your app doing way too much heavy lifting. Then there's GC pressure, when you're creating so many temporary objects that the garbage collector is constantly freezing everything to clean up the mess. Third, lock contention, a classic. Your threads are basically tripping over each other, all trying to grab the same resource at the same time. And finally, IO wait. This one's sneaky. Your app isn't even working. It's just sitting there, waiting. Each of these has its own telltale sign, and you need a specific profiler flag to catch him in the act.
Okay, so those categories are a great starting point. But in the real world, these bad guys have names. They show up as specific, recognizable patterns. So let's open up the case files on 3 of the biggest offenders you're going to run into in your Java apps.
First up in the interrogation room, the Jackson Tower. I bet you've seen this before. The symptoms are classic. Your CPU is completely maxed out. Your API endpoints feel like they're crawling through mud. But when you look at your own code, your own business logic, it seems totally fine. So what gives? And here's the smoking gun. The Flamegraph shows this enormous, wide tower just dominating the whole view, and it's filled with methods from the Jackson JSON library. What this is screaming at you is that your application is burning a massive amount of CPU just turning Java objects into JSON strings. That's it.
So how do we take this tower down? First off, stop sending everything. Use view objects or DTOs to serialize only the data you actually need. Second, and this is a big one, we use your object mapper instance. It's thread safe, and creating new ones over and over is super expensive. And hey, if it's just internal services talking, why use JSON at all? Switch to a much faster binary format like protobuf.
All right, next case file. Let's talk about the logging plateau. Here, the app just feels generally slow, but the real clue is that memory usage is creeping up, and you're seeing these frustrating, totally unexplained pauses. That's the garbage collector working overtime.
Now, the smoking gun for this one is pretty wild. You run an allocation profile and you see this wide, flat plateau, just tons and tons of string operations. And the culprit? It's often a single debug log statement. You see, even if your debug logs are turned off, something like log.debug user plus user still has to create that new string before it even checks the log level. It's generating tons and tons of garbage for no reason.
The fix here is so simple. It's just a change in your coding habits. First, always use parameterized logging, with the curly braces. That way, the string is only built if the log level is actually enabled. No waste. Or, if you have a really complex message to build, just wrap the whole thing in an if log.isDebug enabled block. Problem solved. And now for our final, and maybe the sneakiest, case file, the connection pool wait. This is the one where your app just hangs. It's totally unresponsive. But you log into the server, you check the CPU, and it's near zero. It's literally doing nothing, and that's the entire problem. Now, you can't catch this guy with a standard CPU profiler. You need a special technique called wall clock profiling, which measures total time, including all that waiting around. And when you use it, the smoking gun is just glaring. You'll see this massive solid block in your Flamegraph where all your threads are just stuck, waiting to get a database connection from the pool.
Okay, so how do you fix this traffic jam? Well, the quick and dirty fix is to just increase the size of your connection pool. That can give you some breathing room. But let's be real. The real fix is usually to hunt down the slow SQL queries that are hogging those connections for way too long. Optimize those, and the problem often just vanishes. And if you want to get really advanced, you could even explore using non-blocking drivers.
So look, catching these villains is a huge win, but the story doesn't stop there. Modern Java, we're talking JDK 21 and later, has handed us this revolutionary new tool that completely changes the game for these kinds of I/O problems.
This really gets to the heart of the old way versus the new way of handling concurrent work. See, traditional platform threads, the kind we've used for decades, are heavy. They're managed by the operating system, and you can maybe have a few thousand of them. But these new virtual threads, they are incredibly lightweight, managed by the JVM, not the OS, which means you can have millions of them. Yes, millions on one machine.
So what? Why does this matter? Well, it's an absolute game changer for any app that spends most of its time waiting for a database, waiting for an API call, like our connection pool wait suspect. Here's the magic. When a virtual thread has to wait, it doesn't hog that expensive OS thread. It just steps aside, lets the OS thread go do other useful work, and comes back when it's ready. It's a massive efficiency gain. And the best part is you can handle this incredible scale with the same simple, easy-to-read blocking code you've always written. It's pretty amazing. Okay, so let's wrap this all up in your official detective's cheat sheet. Here it is, the 4-man problem types, their classic symptoms, and the exact profiler command you'll need to generate the perfect Flamegraph to catch them red-handed. This right here, this is your go-to guide for starting any performance investigation.
So there you have it. You now have the tools, you have the techniques, you can finally see exactly what your code is doing under the hood. You can read the clues, you can identify the suspects, and you can find that smoking gun. So the only question left is, what performance bottlenecks are hiding in your code, just waiting for you to find them?